So, good evening, all of you. Welcome to this fourth session on the problem solving session for engineering metrology as a part of the NPTEL program. This course is being instructed by Professor J. Ramkumar at IIT Kanpur. My name is Abhinav Sharma. I am a PMRF fellow and I'll be taking you through this session today. So let us begin directly. In the previous lectures, we have dealt with what is measurement, what are measuring instruments, what are the properties of different measuring instruments like least count and resolution, accuracy, precision. We have seen all this. Then we dealt with in detail about the vernier calipers and micrometers type of instruments. So now today let us move ahead and this is a gradual shift from where we are going from mechanical instruments towards digital instruments, how this transition happens and what all are the different parameters that we need to take care of while designing such an instrument that can give us digital readings. So let us begin for today. So to first understand uh, measurements in digital form, let us understand process control first. And why is it important to understand process control? Because every instrument in its core will be doing some calculations, and based on those calculations it will be giving you some output. So there is an input, after some processing there is an output, and it is the general convention to call such a system a control system, a simple open loop control system wherein we have input, we do some processing, and we yield an output. So this simple block diagram is of a process control block diagram, and here in the instrument the processing that we are doing is called as calibration. After calibration there are simple other processes, several processes like that of amplification, rectification, that we will see in detail in the class now. So let us say we are designing a measurement system. In the previous class we have seen that a measurement system or a measuring instrument has two outputs that we have classified as true value and measured value. And based on these two values, we were calculating the errors that were being generated in the instrument. Now, with these two values and the value of the error, we are pretty sure that if we have to design a measurement system, we need to compare our value to a standard value. This is the standardization that is sometimes called as calibration, and in other terms we call it as error rectification. Now, how do we do this? How do we design such a system that is capable of doing these processes for us inside the instrument, and how do we correlate it with errors, and how do we assure that the answer that it is giving is reliable. So the devices that are used to do this are called comparators. Now, if I try to define this comparator in terms of a block diagram, this comparator can be so. If we want to understand what a comparator should be, a very simple block diagram can be represented in the form of this, wherein it receives an input signal, it compares it. Now this minus sign that we have used here is not necessarily a subtraction, it is just the additive comparison of the standard value with respect to the input. Now what is this additive comparison means? Now this additive comparison is always like, say we are getting a value of pressure to be 5 kilopascals. Let us suppose this is our comparator and it is giving a value of 5 kilopascal here. The standard that we use to compare it is giving a value of, say, 5.1 kilopascals. Now the difference here is 0.1 kilopascal. Should it be plus, should it be minus? This depends on how do we address the input as. Now what does this again means? How do we address the input? Whenever there is a comparison, we need to make sure that there is a reference value to which the data is being compared. We can see this with the help of a graph also. Like if we have a curve like this and this is my zero line and this peak corresponds to, say, 3.3. Now if this is my reference point, then let us say this curve starts from here and not the shifted one. So this peak corresponds to, say, 3.3 volt in reference to this 0. So if this is my point of reference, then the peak will be 3.3 volt minus 0 volt is equals to 3.3 volt. But suppose if I say that my reference standard lies here, which is 1.1 volt. Now all the values above are positive and all the values below are negative. So in the first case, when we were taking the reference point to be 0, in that case the answer was 3.3 volt. But now if we say in the second case my reference point is this, so what happens is the value of the peak will reduce down to 3.3 volt minus 1.1 volt, that is equals to 2.2 volts. So there is the same peak, but the answer that we are getting is different because we have changed our reference standard. We have changed our point of comparison. We have changed our comparator. Now let us see another example in the same graph. If this is my reference point and this is minus 1.1 volt, now 3.3 volts minus 1.1 volts, so this becomes 4.4 volts. Now this same peak, when it is being measured from here at this point, this will give you a value of 4.4 volts rather than 3.3 volts. And again, in the same curve, if I take my standard of reference over here and suppose I want to measure what is the potential over here, now in this part of the graph there is no value here, so the standard reference can be made from this point, or if we take a DC line of 3.3 volt here and we want to measure it from this point, our point of inflection, that is minus 3.3 volts here. So in the fourth case we will get the peak to be 3.3 volts minus 3.3 volts, that will correspond to 6.6 volts. So this is a very important point while designing your comparators. How to set the point of reference. Now if we move on and try to understand that how do we deploy this comparator inside our instrument to do the readings, the first and the foremost thing that we should know and that we have seen till now is that when we design the instruments, the input that we receive is always in the form of analog potentials. Now what does this mean and how are we going to deal with this? See, in the previous classes we have seen that the major units that we try to measure with our measuring instruments are pressure, temperature, kinematic parameters or values. So these kinematic values can be the speed, acceleration, so on and so forth. force. Now these days we do a lot of study on things like humidity, air quality. So this air quality can be measured in terms of VOCs, and so on and so forth. So this is the list of values that we do measure with different measuring devices. Now, how do we see these values, and how is our instrument going to see these values? Now, say if you are walking on a mat, let us suppose this ground or mat is here, and a person is walking on this ground. Now, every time he takes a step, he exerts some amount of pressure on the ground. Now, when he exerts some amount on the pressure on the ground, how is he exerting the pressure? That pressure is being exerted because of the body weight of the person, the speed of walking, and of course the pattern of walking. When I say the pattern of walking, I mean that there might be people who want to stay in a single foot for a longer duration of time, and other people might release their foot early. So the amount of pressure that they exert will vary. Now let us say there are two people, P1 and P2, and we can draw a comparative analysis over here, that in the first instance P1 exerts say x1 pressure, P2 exerts x2 pressure. Now this can be anything. In the next slide, in the next stride, when he walks, this becomes x1 minus something small x, and this becomes x2 plus something small x, and this is very random, completely random. There is no logic associated with this. In the next, it becomes again x1 minus x, this becomes x2 plus x. In the third, it becomes x1 minus x, it becomes x2 plus x. In the fourth, it again becomes x1 and it remains x2 plus x. In the fifth, it remains x1, it remains x2 minus x. Now, how are we getting these values x1 and x2? These are all by our measuring instrument. Fine, our pressure measuring instrument is giving us all these values. So there was a time when we used to do all these studies with the help of mechanical devices. But with the advancement in electronic technologies, we have moved towards electronic instruments. And in the core of these electronic measurement instruments, there is a thing that is called as transducers. Now we will go on to these transducers in the next slide. But before, let us understand the pressure graph that we were trying to build. So at different time instances, what happens is, let us plot a graph of this and say this is the pressure in kilopascals and this is the time in seconds. So at t is equals to 1 instance, this value was x1 and this value was x2. So P1 exerted the value x1 and P2 exerted the value x2. At t is equals to next instance, say t is equals to t2, it exerted something x1 minus very small value x, and it exerted x2 plus something small value x. Then at time instant t3, it gave a value again x1 minus x, and it gave a value x2 plus x. At t is equals to t4, it gave us a value x1 minus x, and it gave us a value x2 plus x. At t is equals to t5, it gave us a value of x1, and this gave us a value of x2 plus x. At t is equals to t6, it gave us a value x1, and it gave us a value of x2 minus x. So it should be somewhere here. Now if we join these dots, we would see that we find a curve like this. And if we join these, we will see that we find a curve like this. Now we can see that in discrete time intervals, there is a continuous variation of input signal. Okay, so if we get a graph like this, and again for pressure we plotted, we can have a graph like this for temperature also, wherein we can say that over the period of 24 hours, the temperature varied like this for city A, and for city B it varied like this over the period of 24 hours. Now these kinds of variation are analog in nature, and we have to measure them using our instrumentation system or measurement system. Fine. So how do we do this? On y-axis, as we have seen, we have values like temperature, pressure, say humidity, elasticity, anything, force. anything that we have on y-axis, and mostly time on x-axis, and we want to plot this y versus x graph. So x is a very clock event. We can put a timer or a clock, and we can keep on counting the time events. This is very simple for us. The problem lies here with y. How do we measure these different values with our devices? So as I said, there is a thing called as transducers. We will introduce it now. Transducers are physical devices that convert physical quantities into electrical signals, precisely voltage, and vice versa. We'll see this in detail in just a moment. So now let us go into depth of what are these transducers, and let us understand what do they do in the system. So as I have written the definition of transducers to be the devices that are capable of converting physical signal or quantities into electrical signals and vice versa, which means the devices can convert either the physical quantities into electrical signals like voltages, or they are capable of creating physical quantities when they are subjected to electrical voltages. Now this is very important to understand here. Let us say this is a transducer, and I apply, say, a force over here. This is a force transducer. So what it will do is it will convert this force into electrical impulses, and it will help us generate analog voltage with respect to time. So every time there is a variation in the force, we see a variation in voltage. So say 1 Newton will correspond to 0.3 volts, 2 newtons will correspond to 0.5 volts, 5 newtons will correspond to 1.05 volts, 10 newtons will correspond to 2.8 volts, so on and so forth. So every time we apply a force to this transducer will create a voltage signal. On the other hand, if I apply a voltage, it should give me the exact same force as an output. Now, how does this happen? This happens by change in physical dimension of device. Let us say we have a cube, cuboid rather it should be called. So now if I am applying force on this surface of the body, what will happen is a compression will start along this axis. Now when this compression along this axis happens, let us say we have one terminal over here as positive and one terminal over here as negative, we see a voltage V variation along with this compression. This corresponds to this part. Now again let us see, we have the same cuboid transducer, and this time instead of applying this force F that we were applying here, this time let us say we take this positive terminal and negative terminal and we applied a known voltage of say X volts. Now if this X volts corresponds to the compression, this body will start to shrink and we will see the dimensions being changed. Delta D. Now if this X volts corresponds to compression, it will compress the device and we will see the body compressing like this. Or if in case this X volts corresponds to a rarefaction, this will go up and this will go down and we will see a rarefaction here. or maybe elongation that you call. So transducers are basically the devices that convert physical quantities into electrical signals and vice versa. Now, how are they going to help us in designing measurement systems, measurement devices? So, because in the retrospect of this course, it is important for us to understand each and every concept in terms of designing an instrument. Now, let us say, if you recall your first class, we have seen an example of a weighing scale. Now, if you remember the conventional weighing scales that were weighing balances, so what it used to do, it used to have one stick, and from its stick, it used to have two parts. One was the quantity to be measured, and the other was a standard weight. Standard weight of say 1 kg, 2 kgs, 5 kgs, whatever it is. And there was suspension in this string. And with this spring suspension or string suspension, we used to balance the weights. And at the point of inflection where both the weights were balanced, we used to say that this quantity is 1 kg. Now again, we were doing a comparison over here. Now this comparison was being held in the form of suspension in the string. Now when we are doing something of the same sort with the weighing scale or electronic weighing scale, we essentially have to do this comparison exercise. No instrument can measure a value without this comparison. We have to always do this comparison, and we always have to do this with the help of comparator. Now this comparator in mechanical systems or conventional systems can be these strings that work in the form of suspension, or a coil that stores energy in the form of recoil coefficients, or damper based systems, whatever. But we will have to store the energy in some mechanical form to do the comparison. This is the work of a comparator. When you design a comparator, mechanical comparator, you have to store the energy balancing in some of the mechanical instrument. Now, when you do this, there is always a chance of energy loss, and while designing very delicate measurements, this might not be advisable. So we see a transition from mechanical systems or conventional systems to electronic systems, wherein both our transducers and comparators are devices that are specifically designed for a function and is essentially an electronic chip. Now let us go on to depth to understand this with the help of an example. And before we go on to an example, let us see a measurement system block diagram. And this measurement system is essentially electronic in nature. So let us begin from the very primary element that we have a input. Now this input is the measurand, the thing, the quantity that we have to measure. Now let us say this is force, and we have the graph of force, say like this. So this force F is varying with respect to time. That's all. And we have to measure this force. Now, when we have to design an electronics based system, we should understand the basics of electronics involved in this. So, and before understanding the electronics involved in this, we should understand the nature of variation in the input. Okay, so let us say the first thing that it hits is a transducer. Although there is some preconditioning done at times, but let's not go into very detail of that preconditioning. Let us say that it directly hits a transducer here. So what this transducer will do, this will convert this force into, so till here we had a force signal, now we have a voltage signal. So this voltage will vary differently now. Now the first and the foremost thing that we have to do here and know in reality what happens is that this voltage signal is of very small amplitude. It's not like for a 5 Newton force you will get a 5 volt voltage. No. The transducer generates, because these are passive devices and not active devices. What is the meaning of passive and active? The devices that use Okay, let us see it here. Active devices are the ones that use an external power source. Sorry. Now, if you go back to the previous slide and you see this example over here, we have not used any external power source. Only there was a force that was generating a voltage, or we were giving a voltage that was generating a compression or rarefaction. But in all this functioning, no external battery was connected, no external power supply was connected to this transducer. So this is a passive transducer. In case to do it function, if we would have used a battery or an external power supply, we would have called it a active transducer. So generally when we talk about passive transducers, we do not use an external power source, and because of that, the amount of voltage that we get because of the force being applied or the temperature being applied, the actual real value of voltage that we get is of very small amplitude. So the second stage of thing that we need to do is called as amplification. Now this amplification enhances the value of voltage, and we get a considerable amount of voltage being seen over here. Now, at times, this is important to understand, though we will not deal with the solution over here, but to understand the overall process, it is important to understand that at times, this signal that we are going to amplify is always mixed with some sort of noise. Now, this noise may be because of the environment in which measurement is being done, or the quality of device that is being used, or maybe because of loose wire connections. This noise can be generated over here. So if we see essentially the output of transducer is usually mixed with noise, that should be avoided. Now let us see this with the help of a graph. Say we have a force variation over here, and we apply it to a transducer, and we get an output in terms of electrical signal. So this V versus T, this would not be something like this. The output of the transducer is always mixed with noises, so we would get a variation like this, and we will not be able to make out that okay, exactly what is this value. Is this 0.1 volts, or is it 0.09 volts, or is it 0.13 volts, whatever it is. So we will always have errors, and these noise are classified into white noise, short noise, instrument noise, whatever. This can be generated because of faulty wires, open ground connections, floating ground problems, so on and so forth. There can be a lot of problems because of this noise is generated, this noise over here. So instead of getting a sharp signal like this, we get a distorted signal like this. So our important step is to remove this distortion due to system generated noises. Hence, the next stage that we design after amplification is called as rectification, or maybe before amplification. Rather, I should correct myself. Before amplification, noise removal must be practiced. Why? Because if there is a noisy signal, so let us write this in terms of mathematics. So x plus minus delta x, x is the actual variation, and delta x is the noise element. Now if this is the signal that is being generated by the transducer and we amplify it without rectification, the noise element will also be amplified along with the signal. So after amplification, let us say this x was to become x bar. Now what will happen is this will become x plus minus delta x bar, and now if we resolve it, this will become x plus minus delta x bar square, or maybe some function, not exactly square, maybe some function x y z, whatever it is. It can be a square, it can be a cube, it can be a linear variation with a multiple, it can be anything. So this element will also get amplified along with this input signal. So we must practice this noise removal over here before the amplification is done. So essentially, as soon as you get the input signal and you pass it through the transducer and it converts into an electrical voltage, the first thing that should be done is noise removal and noise rectification. And after that, we should go on for amplification. A very clean signal that we get should be amplified. Is this understood till here?
Yes, sir.
Okay. So we will continue with this in a short time. Let us break for 1 or 2 minutes and then we'll start again. Okay, so now let us take up an example of a transducer system. So essentially what we have seen is that a transducer is a device that converts energy from one to the other suitable form. Now, why do we call this suitable form? Because voltages and currents are easy for us to pre-process and understand. So, let us go ahead and understand this with resistance based transducer. We had seen an example previously that there is a fellow who's walking on ground. Fine, and he is exerting some amount of force on the ground. And while he exerts this force on the ground, there is a reaction force that is being exerted back on the body. Okay, now this is a very important health parameter also, and doctors also want to know that how much amount of force is being reflected back to the body while a person is walking. So we need to design a system such that we can measure the forces that a body exerts on the ground while walking, and as it does so, what is the reaction force that is being exerted back to the body. So let us see how can we measure forces using these transducers. So there is a very simple device that is nowadays available on a commercial basis also, and in terms of concepts also, which is called as a force sensitive resistor. In short, we call it as FSR. So what it does is, this is the actual packaging of a FSR resistor, and on this portion a flexible material is mounted. Now what happens is, as soon as you apply force onto this surface, these two terminals, they start to change their resistances. Now suppose the original resistance was R. Once this force is applied, this R was with no force. As soon as a force F is applied, this R will change to R plus minus delta R corresponding to F. If F1 force is applied, the resistance will change up to R plus minus delta R F1. So every time you apply a force, the resistance will change, and hence it is named as a force sensitive resistor. So if we go on to the depth of understanding the concept of resistances, in the very beginning we said that if R is the resistance of this wire, we can write R as rho R L upon A. where L is the length of the element, A is the area of the surface, R is the resistivity, which is the property of the wire, and this is some coefficient of multiplication. So every time the length and area of the wire changes, the resistances changes. So if we have a system like this, which has some output resistance, now if we apply force over here, and you know force is equals to pressure into area, or rather pressure is equals to force per unit area. So this force is invariably connected with the area, and as soon as you change the area or you change the force, this parameter will start to change, and when it will start to change or length will start to change, eventually the resistance will change. So it is interesting to understand here that though we were changing the force, we eventually turned out to change the resistance of the body. And now this resistance is being calibrated in terms of voltages. This is how a general transducer action is being taken. Now this can be understood in terms of different other things. We have changed the resistance here. We can change different other parameters of a body by changing the input applied to that particular resistance based transducer, or whatever kind of transducer we are making. A very basic example of a transducer is a piezoelectric signal or a piezoelectric crystal. You might have seen in your analog watches there is a very small button kind of a thing that is used as a, and it is also called as button cell at times. This battery is made up of a piezoelectric crystal or a quartz crystal, and hence at times you would have seen in your analog watches it is always referred to as quartz. So what this quartz does is it has a natural tendency of oscillations. Now when these oscillations are there, then the natural tendency of oscillation is means you don't need to give an external supply to this to generate oscillations. There are quartz particles that keep on oscillating up and down, up and down, up and down like this, and because of these oscillations it generates a force, and that force is eventually converted into a voltage, and that very small voltage is used to run your analog watches. This is a very simple example of a force to voltage conversion. But here, this is not being used conventionally as a transducer. Quartz crystal used as a cell in analog watches is not a transducer. Where else do we find the application of a piezoelectric crystal or a quartz crystal is our microphones. So you might have seen your mics being made like this. These kind of mics. Now here, when you open up this black portion, you would find always there is a small round circular thing. So what we are actually giving as input is sound, and this sound is eventually the force that is being generated as we speak. So there is a movement of air particles that start to oscillate in a specific pattern at a specific frequency, and when it reaches your eardrums it creates the similar frequency pattern based out of which you can listen. Now similar thing is being done with this microphone. This crystal over here, or the piezoelectric crystal over here, it reads these force patterns, and without the help of an external battery source, these force patterns are amplified by this piezoelectric crystal, and it generates a higher voltage that is used to amplify the sounds. Okay, so these are general examples of transducers based systems. We will end up our lecture over here today, and in the next sessions we will take up on different kinds of transducers based systems and a few numerical based problems, so that we will be able to design our systems specific for our cases. So for today we will end up our lecture. If you have any queries, you can post on to my email and we will be glad to solve your questions after this. Thank you.